Hello, this is Joe Trout, and we wanted to continue our discussion about stars and the HR diagram. So if you remember, if we look at the main sequence stars, we said that they are, if we plotted luminosity versus temperature or um, or star type, we said that um, most of the stars are on this main sequence here. And if we look at the main sequence, we see that on the HR diagram, if we look up in the upper left-hand corner, these are the bright hot stars, and in the lower left, these are the lower or the faint and cool stars. And don't forget, we have temperature decreasing as the x-axis increases, right? And this is the luminosity as compared to the sun. And we said that on the main sequence stars, they're also called dwarfs, and they're your normal run-of-the-mill stars, and about 90% of our nearby stars are main sequence stars. And in the HR diagram, this band, as we said, um, bright and hot, and faint and dim. Our sun is a MS type star type G2, and we'd end up somewhere around here, right, with the luminosity of 1. And then the cool MS stars are more common than hot main sequence stars. We also have the giants. They're much bigger than the sun, so 10 to 100 times larger. And we have the red giants, which are the coolest. They're about 4,000 Kelvin, and they're the coolest giant stars, and they appear very red. The supergiants are both bigger and brighter than your average giant. So I end up in this region of the HR diagram. So here we see the atmosphere of Betelgeuse and the size of the stars, and we look at the size of the Earth's orbit, and we look at the size of Jupiter's orbit. So the size of this star is larger than the orbit of Jupiter. So if we look at white dwarfs, they're much smaller than the sun, and they're very hot but not very bright. And they're actually remnants of dead or dying stars. So here we see some white dwarf stars in M4, and here's where the Hubble telescope actually was able to pick them out. Okay, so we know that there are hot blue massive stars and cooler red less massive stars, and let's talk about their lifetime. So what happens over time? So while a star is stable, there's something called the hydrostatic equilibrium, and we said that fusion creates a pressure that pushes out on the star's surface. And we have gravity that's pulling in. And if it's in hydrostatic equilibrium, the pressure that's pushing out equals the gravity that's pulling in, and the star doesn't change. And at first, all stars process hydrogen into helium. And if we look at birth, they're mostly hydrogen and a little bit of helium. And then as time goes on, what happens is the core is hotter and it's fusing hydrogen into helium. So we're getting more and more helium in the core, and less and the same amount as you move out from the center. So after about 10 billion years, right, our core here, where this dotted line is, starts to become just helium. So we're starting to run out of hydrogen in the core, where things are fusing. So eventually, as the hydrogen in the core is consumed, the star begins to die. And its evolution from then on depends very much on the mass of the star. So low mass stars tend to go quietly, and high mass stars tend to go with a big bang. So as the fuel in the core is used up, the core contracts. And when it's used up, the core begins to collapse. And that collapse releases gravitational energy, and the layers just outside the core heat up. So we start running out of fuel. So now gravity starts to win because the pressure isn't as great, and it starts to collapse. But the collapse releases energy, and the layers just outside the core begin to heat up. So then the hydrogen begins to begins to fuse outside the core because it's getting hotter. So if we look at our low mass stars, we have an initial giant stage where with the red giant branch. So what we see is that as the core begins to shrink, the outside layers of the star expand and cool. So they'll start to move in this area. And despite its cooler temperature, its luminosity is increasing enormously just because it's big, right? So think of it this way. You can have maybe 1,000 watt bulb in your lamp. Or you could have 2,100 watt bulbs, right? So the 2,100 watt bulbs are going to take up a larger area, and they're going to be brighter even though the individual bulbs are not that bright. Okay, so now a red giant is as big an orbit as Mercury, and once again, despite its cooler temperature, its luminosity increases enormously due to its large size. So it moves off the main sequence, and starts to end up as a red giant. Next, it goes into this horizontal branch along the next giant stage, and that's when core helium is burning. And once the core temperature has reached 100 million degrees, then helium in the core starts to fuse. And as helium begins to fuse extremely rapidly, and within a few hours, the enormous energy output is over, and the star once again reaches equilibrium. So the gravitational force pulling in is equal to the pressure that's pushing out. And these are evolution of sun-like stars, right? About the same size as the sun. And as the helium in the core fuses to carbon, the core becomes hotter and hotter, and the helium burns faster and faster. And soon all the helium in the core has been converted to carbon. And again, the core contracts and collapses, releasing gravitational energy. Then we get the final giant stage, the asymptotic giant branch, or the supergiant stage, and the shell helium fusion. And the helium is fused in the first shell, and hydrogen in the next. So we get something that looks like this. So this is the Earth's orbit, and if we look, this is 300 million kilometers, right? And inside, in the core of the star, we have a carbon-oxygen core, and then we have a helium fusing shell above it, and then we have a dormant hydrogen fusion shell. So these low mass stars are not massive enough to turn carbon and oxygen cores into heavier elements. So it's pretty much done creating elements with carbon and oxygen. And these stars eject most of their outer layer. And only the core is left, which then lights up the gas, and the star has been ejecting, causing something called a planetary nebula. So the core continues to contract, but never gets hot enough to burn carbon. And meanwhile, the outer layers of the stars expand as a planetary nebula. Right, so this shows the core, and here's the outside exploding away. So here's another picture of Helix Nebula and NGC 6826 and 7027. So now we're in the phase that even after the nebula has dispersed into space, the core remains. And it's extremely dense and extremely hot, but quite small. And this star is called a white dwarf. So it started on the main sequence, moved out to this red giant stage, then the horizontal branch, then we go up, planetary nebula, and down to the white dwarfs phase. And white dwarfs are very hot, but not very luminous. So they're in this area. High temperature and low luminosity. And the white dwarf, is the burned out carbon oxygen core of the dead star. And it's supported by something called electron degeneracy pressure. So this is the idea. Remember before, what we had was hydrostatic equilibrium. There was fusion going on, it was really hot, pressure would push out, and gravity would pull in. Now in essence what happens is we get so close that the electrons are actually pushing against one another. So you call that the electron degeneracy pressure. So if it's less than 1.5 times the mass of the sun, then they form from main sequence stars between about 0.8 and 8 times the mass of the sun. So we have a white dwarf, and the smaller star is Sirius B, and is a white dwarf, and it has a companion star A that's much brighter. And as the white dwarf cools, its size does not change much. It simply gets dimmer and dimmer and dimmer. Once again, due to this electron degeneracy pressure. So the electrons are actually pushing against one another. So the Hubble telescope has detected white dwarf stars in globule clusters, and they're shown circled in blue on the right hand side. So more massive white dwarfs are blank compared with less massive white dwarfs, and we have hotter, smaller, larger, cooler, and identical in size. All right? And what we find is that more massive white dwarfs are actually smaller. So we've shown that the more mass will squeeze a white dwarf into a smaller volume due to this electron degeneracy pressure. So a smaller white dwarf is actually more massive. So let's look at the low mass summary. We have giants. After the core hydrogen burning, and then we get first a shell hydrogen burning for normal giants, then second core helium burning, that was that horizontal branch, and then third is shell helium burning, the supergiants, and then most go through an unstable variable stage, and the white dwarfs are the collapsed remnants of a low mass star. So we start with a protostar. We start with a whole bunch of dust and gas that's laying around. Gravity pulls it together, it starts to collapse. It ends up on the main sequence where the hydrostatic equilibrium is going on. Then we go into the red giant phase, excuse me, where it all of a sudden starts to expand, and well, after contracting, and then finally we end up with the white dwarf stage. So the star formation is cyclical. So a star forms, evolve, and die. And in dying, they send out heavy elements into the interstellar medium, and these elements then become parts of new stars. So the relative size and colors of a normal G-star, such as our Sun, during its formable stage on the main sequence and while passing through the red giant and white dwarf stages. Right, so it starts as a protostar, it gets smaller and smaller, it gets into the main sequence, then it starts getting a little larger and larger because it gets into the red giant stage and then the white dwarf, and then it's starting to get to its end of its life. So at maximum swelling, the red giant is 70 times the size of its parent, right? And the core is about 1/15 the size of its parent. So here we are on the main sequence. This is the parent star, if you will. And now this is 70 times as big, but its core is much smaller. This shows a picture of one of the nebulas, and this is an hourglass nebula. So the double lobe shape created by the dense ring, which funnels material to either pole, right? So we can see we get most of the expansion in these directions. So we could also come up with a nova. So we have a mini explosion that can occur when a white dwarf is in a binary system. So the idea is that the white dwarf can steal mass from its neighbor, and the extra mass makes the white dwarf temporarily unstable, and a mini explosion occurs. And this process can repeat itself. So here we have a nova is a star that flares up very suddenly and then returns very slowly to its formal luminosity. So we have the white dwarf and its companion star, and what's happening is the main sequence star has some mass coming off of it, and it's absorbed by the white dwarf. Okay, so that's pretty much what happens with low mass stars. So next we'll talk about what happens with high mass stars.